Hello, this is mathjazz from Almost Cool. This playlist is a series of projectile motion problems. It assumes that you already know how to take derivatives, find antiderivatives, and how to optimize or find maxima or minima of various problems. These problems are very typical of a first semester calculus course, as projectile motion is fairly easy to describe and examine using the techniques of differentiation and anti-differentiation. So these problems are given in no particular order, but they're just very typical projectile motion problems for first semester calculus students. Here is problem 1. Suppose that a ball is thrown off of an 8-meter cliff with an upward velocity of 15 meters per second. Suppose that wind resistance is negligible and that gravity is 9.81 meters per second. A. How long does it take from the time the ball was thrown for the ball to reach its maximum height from the bottom of the cliff? B. How high off of the bottom of the cliff is the ball at its highest point? C. How long after being thrown does the ball hit the bottom of the cliff? And D. If the horizontal velocity of the ball were 3 meters per second away from the cliff face, how far would the ball be from the base of the cliff? Pause the video now to work out your solutions, and when you're done, unpause the video and I will go through those solutions. 1A. To maximize height, we will first need to find the zeros of the velocity function. That is because the velocity function is the derivative of the position function, and we're trying to maximize position here. So we don't know the velocity function, but we do know that it is the antiderivative of the acceleration function, and one other thing we know is that gravity is the acceleration function for projectile problems. So we know that a of t equals negative 9.81. We take the antiderivative to get v of t equals negative 9.81 t plus c. Note that we are actually making a choice here in this problem of having down be the negative direction. This is a very typical orthodox way of doing these problems. You could get the same answers if you chose up to be the negative direction, so long as you were consistent in your choice of up being negative. But we're going to do this problem in the most typical way possible. Down will be negative, the bottom of the cliff will be height 0, and the time when the ball was thrown will be time 0. There, of course, you could pick any time you want it to be 0, and as long as you were consistent, you'd get the same answer. You could pick wherever you wanted to be height 0, and as long as you were consistent, you would still get the same answer. But those are the three choices we're going to make in this problem, and that was just a note to say that that's one of the choices we're making. So we get the general antiderivative is velocity at time t equals negative 9.81 t plus c. Since we want, again, these are the choices we're making, that the throw is at time 0, that means that the velocity at time 0 must be 15, because we were told in the beginning of the problem that the velocity was upward at 15 meters per second. So we choose positive 15 to be the value of v at time t equals 0. So we plug those into our velocity function, getting 15 for the velocity equals negative 9.81 times 0 for t plus c is our constant that we got from anti-deriving. And so we get that c is 15. So our velocity function is v of t equals negative 9.81 t plus 15. If we had chosen either up to be the negative direction, or if we had chosen time 0 to be somewhere other than the time of the throw, we would get a different value for c, and that different value for c would allow the answers at the very end of the computation to match up with the answers we get from making the choices we did. So it's built into the very nature of taking an antiderivative to make, as long as all of the choices are consistent, to get the same answer regardless of what choice you make. In fact, it might be interesting to try that, to define maybe time 1 is the time of the throw, and resolving this problem and seeing how you'd still get the same answer for all of these questions. But that's for another video. We'll now find the roots of v of t so that we can find the critical points of the position function. We set v of t equal to 0 and solve for t, giving t equals 15 over 9.81. This is in seconds, as 15 is in meters per second, and 9.81 is in seconds, so they cancel and give us the correct unit. Sorry, 9.81 is in meters per second squared, so the meters and one of the sets of seconds cancel, leaving seconds. So it takes 15 over 9.81 seconds for the ball to reach its highest point, and that gives us the answer to part A. For part B, we already know what time the ball hits its highest point, so if we just get the height function, then we can plug in the time and get the maximum height. And to find the height function, we're going to take the antiderivative of the velocity function. I say correct antiderivative because, of course, when we take the antiderivative, we'll get a whole family of functions with a general constant, and then we'll do the same thing we did in part A to solve for a specific constant that will work for this specific problem. So we take the antiderivative of v of t to get negative 9.81 over 2 times t squared plus 15t plus our constant of integration d. We could have used c again, but I'm choosing to use a different letter just to reduce confusion. We're not going to reuse the same letter. But, of course, you can reuse c if you choose, so long as you don't accidentally mix up the two c's from the two different parts. The height of the cliff is 8 meters, so we want the position of the ball at time 0 to be 8 meters, which means that we want p of 0 to be 8. So we set 8 equal to p of 0, which is d, so d equals 8. Plugging in our time from part A, we get p of 15 over 9.81 is 8 plus 225 over 2 times 9.81. And we won't bother to simplify. But that is the position of the ball at its highest point. And that is the distance from the bottom of the cliff to the position of the ball, as opposed to being the height from the distance from the top of the cliff to the position of the ball. It's the distance from the bottom of the cliff. C. How long does it take for the ball to hit the bottom of the cliff? So we have to figure out at what time does the position equal 0, because we already decided that the position 0 would be set at the bottom of the cliff. So that means that when p equals 0, we have hit the bottom of the cliff. So we just set the parabola we got from part B equal to 0. P of t equals negative 9.81 over 2 times t squared plus 15t plus 8. We use the quadratic formula to set that equal to 0 and solve for t. And we get t equals 15 plus or minus the square root of 381.96 divided by 9.81. However, since the ball was thrown at time 0, it cannot have arrived at the ground before it was thrown. I mean, I guess the ball may have been sitting on the ground before it was picked up, but our equations don't actually describe the ball's motion before it was thrown. This is a projectile motion equation, and before the ball is thrown, it's not in projectile motion, so the equation does not describe the movement before time 0. Therefore, we throw out 15 minus the square root of 381.96 all over 9.81, because The square root of 380 something is bigger than 15, so 15 minus that number is negative, and that means that that time is before the ball was thrown, so before the equation applies. We throw out the negative answer, we get t equals 15 plus the square root of 381.96 over 9.81. That is the time at which the ball hits the bottom of the cliff. Part D, how far is the landing point of the ball from the base of the cliff? Now for this answer, we multiply the time the ball took to travel by the horizontal speed of the ball. So 3 is how fast the ball is going in meters per second, and the number in the parentheses is the time that the ball traveled. And that'll be our answer. That's the distance the ball traveled horizontally. Now, the more interesting thing is that's exactly what we get if we integrate the horizontal velocity function, that is, horizontal velocity equals 3, over the time interval 0 to the time of impact. Like so. This is just the integration of a constant, so I'm not going to talk a whole lot about this computation, but notice that it is in fact the same number for both multiplying time by speed as integrating the speed over a time interval. And that actually gets us to the next point, which is if the velocity were not constant, then the calculation of the horizontal distance would require integration to solve. Multiplying the velocity function by the time that the ball traveled would not give us the right answer. Integration of the velocity function over the correct time interval would give us the right answer. And this leads us into the next note that part D is actually a multivariable calculus problem. We dealt with a vertical variable and a horizontal variable in time. So this is actually an example of a multivariable calculus problem that we were able to solve using single variable calculus methods by dealing with one variable at a time. And it turns out that there are a lot of multivariable problems that are solvable using only single variable calculus techniques. Although there are several that are not possible to solve using single variable calculus techniques. And that's what you'll probably dwell on in a multivariable class, is stuff that you could not do with only one variable calculus. However, it is interesting to note that there are several multivariable type problems that are solvable using calculus on one variable at a time. Thank you for watching this video. Email, website, and Facebook information are on the screen, as well as in the description of the video down below. Feel free to contact me on topics for future videos, ask questions, or to tell me about errors in the videos. And I hope that you're enjoying learning calculus. Have a great day.